Good morning. Let's begin. Don't get distracted by this picture. This is part of the Christmas decoration. I need it later, but I thought it's so beautiful that we should have it all the time here. However, I need some light here. So, let me briefly repeat some things that we did last time. Remember, the goal was we wanted to understand how electromagnetic radiation can propagate through a magnetized plasma. And now, of course, we have the trouble that the magnetic field imprints a preferred direction into the plasma, and that the situation becomes much more complicated than it used to be in a thermal plasma that otherwise had no preferred direction. So we added some simplicity somewhere else. We neglected the thermal motion of the electrons in comparison to the motion induced by the Lorentz force, and said, okay, from now on we are dealing with not only a magnetized, but a magnetized and cold plasma. And so we did not have the Liouville equation, which is a kinetic equation for an ensemble of electrons, as our starting point, but we had the equation of motion for an individual electron as a starting point. Right? Because statistical properties of the electron ensemble do not play a role now because we are focusing on a cold plasma. So we just had the equation for the Lorentz force, and we did what we always do. We decompose this into plane waves in order to in this case, in order to remove the time derivative and replace the time derivative by a multiplication with the frequency. Then we had a matrix equation that we just needed to invert, and we did that, and so on and so forth. And the goal is always, as it has been for a warm plasma as well, that we want to understand how electromagnetic waves can propagate. And for this, we need to have the dielectric tensor epsilon, so that we can see under which conditions this equation is solvable, right? Except by E equals 0. So last time we found then that we have a dielectric tensor that looks like this. So now we have three contributions. We have a contribution whose geometry is set by the parallel projector with respect to the magnetic field, and the little b with a hat is the unit vector into the magnetic field direction. My perpendicular is the complement to it. And we had a third matrix B now, whose components are given by the Levi-Civita symbol. And remember how this came about. This came about through the magnetic part of the Lorentz force, which contains a vector product between the velocity and the magnetic field, and this is how this antisymmetric contribution came about. And very much of what we are going to talk about today comes from the antisymmetry of this contribution here. Right? This will lead to magnetic birefringence of plasma, and so on and so forth. Okay, several functions. We saw that epsilon parallel is given by this nice expression here, epsilon parallel, 1 minus omega p square divided by omega square. And omega p, as always, is the plasma frequency. And we had omega perpendicular, and that was this thing here, 1 minus omega p square divided by omega square minus omega L square, and omega L is the Larmor frequency. So the the frequency with which an electron gyrates around the magnetic field. Okay, and we had a third function, g, and this was this thing here. Okay. And now you see that there are evidently two directions, two preferred directions in this matrix here. The direction of the magnetic field, the direction of the wave vector k of the incoming electromagnetic field. And this means that a clear distinction between longitudinal and transverse electromagnetic waves is now no longer possible, right? Because once you have the electromagnetic field longitudinal or transverse with respect to the magnetic field, it will not be with respect to its own wave vector k, and then it won't remain longitudinal or transverse. So let's simplify this a bit and say, okay, I now want to analyze situations in which the electromagnetic radiation propagates along or against the magnetic field. So then k hat, right, the unit vector in k direction would be parallel or antiparallel to the magnetic field, and then this thing here would also be the parallel projector with respect to the magnetic field. Okay? So this is now the specialization for k parallel to b. So now we have a magnetic field somewhere and the electromagnetic radiation runs against it or with it. All right. I'm doing that for simplicity, of course, right? If you wanted to analyze the situation generally, it's much more difficult. But I'm aiming at discussing Faraday rotation, magnetic birefringence, and for that I need exactly this situation here. Okay, then I can write the whole situation as epsilon parallel times pi parallel plus wait a moment. Let's write the whole matrix now. So the parallel part is not going to change. The perpendicular part is going to be 1 minus omega square over c square k square epsilon perpendicular pi perpendicular, and we have minus I times omega square divided by c square k square g times b. Okay, well, we had something very similar last time already. Now, I'm going to fix k such that it points into the z direction, and then of course b will also point either with or against the z direction. And I'm choosing both of them such that they point in the same direction. Okay, so then the parallel projector is going to be this spectacular thing. The perpendicular projector is this. And now the matrix B is simply this thing here. It's B hat has a single component, that's B3, which is 1. So the only elements of that curly B matrix that can be set, that can be different from 0, must have indices 1, 2 or 2, 1. Okay. All right. Now let me write this down. So we have the following matrix: 1 minus omega square over c square k square epsilon perpendicular. Same appears here because of these two entries. Okay, then I have minus I omega square over c square k square times g up here, and plus I omega square over c square k square times g over here. Then I have minus omega square c square k square epsilon parallel down here from this contribution, and the rest is zeros. Aha! And now we need to have a vanishing determinant of the whole thing, right, for allowing non-trivial solutions. I don't care for the longitudinal mode now. Now, of course, we do have a longitudinal mode, right? Because now we are aligning the wave vector direction with the magnetic field. The longitudinal component will propagate only if epsilon parallel is 0. If epsilon parallel is 0, then the frequency is going to be the plasma frequency and nothing else. Okay, boring. Now let me look at the other part, the transverse direction here. So for the determinant of the whole matrix to vanish, either this thing vanishes, which I now want to exclude, or the determinant of that must vanish. So for the case that I'm now only considering, this subdeterminant must vanish. Now, this would be the square of this one, of these diagonal elements, minus the product of these. But they are negatives of each other, but they have a factor of I. So I can write this condition as this. Okay, the difference between them must be 0, and all right. So now I can take the square root. And now these two signs appear, and this is beautiful. And from here I get c square k square equals omega square epsilon perpendicular plus or minus g. We had all of that last time, just with angle information within it. And epsilon perpendicular plus or minus g can be simplified to read, and we had this last time already, so let me briefly write this down. This is just omega p square divided by omega plus or minus omega L. Okay, now we have our dispersion relation. And first of all, I would like to have some fun with that. Okay. Let me now assume that we have frequencies omega high compared to both omega p and omega L. And let me therefore give you some numbers. So if you calculate the Larmor frequency, that goes like this. That's 17.4 megahertz. If you have a magnetic field of 1 Gauss. And 1 Gauss in astronomical terms is a really, 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 really strong magnetic field. In a typical galaxy cluster, you have magnetic fields of order, let's say, a microgauss. So this is of order 17.4 Hertz. This is really slow. Omega p, we had this before. That's about 56 kilohertz. If you have an electron density of 1 per cubic centimeter. All right, suppose you have a milligauss or so, like you would have in a galaxy, maybe a spiral galaxy, such as the one that I'm showing to you. Then this would be in the kilohertz regime, and this would be in the kilohertz regime. So if we are in a typical radio regime around megahertz or so, we have a situation in which the frequency is very much, frequency omega is very much higher than both of them, right? The Larmor frequency and the plasma frequency. Okay, so this legitimates doing the following thing. I take the square root without any approximation on the left-hand side. And now I have to do that. This is still exact, of course, and now I will make use of omega being much larger than omega p and omega L. So I'm writing this as omega p squared divided by omega squared. In other words, I'm pulling a factor of omega out of these brackets here, these parentheses. And what then remains in the parentheses is 1 plus or minus omega L divided by omega. And omega L divided by omega is again a small number. So let me write this as 1 plus or minus omega L divided by omega. Aha. But now I've made an approximation. Right now I've used the usual Taylor approximation that 1 plus or minus something small, 1 over 1 plus or minus something small doesn't matter, but I should revert the signs here. Okay? Right, so, I can write this obviously as 1 minus omega p squared divided by omega squared. Now, plus or minus omega p squared omega L divided by omega cubed. Now, both of these contributions are small. Let me now approximate this one step further and say this is approximately omega 1 minus omega p squared divided by 2 omega squared plus or minus omega p squared omega L divided by 2 omega cubed. Right? Using the Taylor approximation for the square root, 1 plus or minus something small, square root is approximately 1 plus or minus something small divided by 2. All right, is this legitimate? I mean, here we have something that has 1 over omega cubed. Here we have something that has 1 over omega squared. Is that still a consistent approximation? It is, because the next order approximation would contain a factor of omega p squared divided by omega omega p to the fourth divided by omega to the fourth power. So if I systematically exclude everything that is of order 1 over omega to the fourth power and higher, then this is the consistent approximation. Okay, so obviously we get k is some k0 without a magnetic field plus or minus some change by the magnetic field. And K0 is omega divided by C, 1 minus omega p squared divided by 2 omega squared. Okay, that would be our dispersion relation in a cold but non-magnetized plasma. Remember, we had a dispersion relation for electromagnetic waves, transverse electromagnetic waves in a non-magnetized but thermal plasma. Have a look what it looked like there. Okay, and delta K, what is this? This is omega divided by C, but now we cancel one of these omegas, so we have 1 over C, omega p square omega L divided by 2 times omega squared. This is the change due to the magnetic field. Now let me insert the plasma frequency, which is 4 pi times the electron number density times E squared, electron charge squared. So if I divide by 2, I get a 2 pi Ne E squared divided by C Me. So this would be omega p squared divided by 2c. Now I have an omega L that I need to take into account. This is EB0 divided by MEC. And finally I have 1 over omega squared. All right, so again, this is omega p squared divided by 2c. This is omega L. Okay. So now we have some constants here. 2 pi E cubed ME squared C squared. They are all constant along the line of sight, but what changes along the line of sight is the electron density times the magnetic field. All right, so let me bundle this in a somewhat different way. Maybe it fits in here. So this would be 2 pi NE E cubed divided by MEC squared. Now we have the parts that depend on location, right, along the line of sight, because the electron density may change, the magnetic field as well. And finally, we have this dependence of 1 over omega squared. So in other words, if the frequency gets very high, delta K will go to 0. Right? At very high frequency, nothing will happen. But at sufficiently high frequency for this approximation to work, and sufficiently low frequency for this effect to be appreciable, there will be 2 branches in our dispersion relation. What do they mean? Now let's go back here. And now I will focus on this submatrix here, and I will go into the subspace perpendicular to both K and B and analyze the then 2-dimensional electric field vector there. Right? In other words, here's my light ray, this is also the direction of the magnetic field. There's a 2-space perpendicular to that, and I'm now going into that 2-space just because it's simpler. And now I know from the dispersion relation that if electromagnetic waves can propagate at all, then of course this dispersion relation must hold. But this would mean that this term and this term are plus or minus equal. Okay? So I'm now writing down this matrix here under the condition that this dispersion relation is satisfied. Otherwise, no signals would propagate in the first place. So this means I can write 1 minus omega squared divided by c squared, k squared, epsilon perpendicular. Because this factor is now appearing everywhere in all 4 elements of the matrix. I can pull it out of the matrix, of course. And what remains is 1, 1, and plus or minus ig minus or plus ig. G is factored out. So now if I'm looking for eigenvectors to the eigenvalue 0 for the transverse propagating mode, I need to satisfy the equation 1 plus or minus I minus or plus I 1 times Ex times Ey. Must be 0. Okay. So I get Ex plus or minus I Ey equals 0. And of course I get the same from the next line. Right? So this means that if I fix Ex, then Ey is given by plus or minus I Ex. Let me write the I here as e to the power of I times pi over 2. Right? To emphasize that this is a phase shift now of pi half between the two and a possible sign flip. Right? So I can write this as e to the power of plus or minus I times pi over 2 is now a phase shift of plus or minus pi over 2 between Ex and Ey. So what does this mean? If you look at Ex, right, this is going to oscillate. And Ey is also going to oscillate, of course. I can't possibly do this, right? But now with the phase shift of pi over 2. And this means if you look at the tip of an arrow that has the components Ex and Ey, this goes round in a circle. Or in another one, depending on whether the phase shift is plus or minus pi over 2. So we have this situation here. Right? We have two circularly polarized modes that are circularly polarized opposite of each other. That's the point. So this means that what we found is the following. First of all, the eigenmodes correspond to circularly polarized waves. And the eigenvalues, in other words, the condition that the dispersion relation has to vanish, attaches two different dispersion relations to the left and right circularly polarized modes. All right, now if you if you think of these two k vectors here, and if you have the spatial part of the phase of the electromagnetic wave in mind, then you see that the k0 just takes care of the phase of these two circularly polarized modes to to propagate, to evolve in the same way. But this one adds to the phase of the right circular polarized mode and removes from the phase of the left circular polarized mode. Right? So both of them take care of an increasing phase shift between the left and right polarized modes. So this means that the right polarized mode is running ahead of the left polarized mode. Now, if you start with with a linearly polarized wave, then you have left and right circular polarized modes with the same amplitude superposed. And now you create a phase shift between the two. And this means that the polarization plane of the waves, which is the result of the superposition of the two circularly polarized waves, is going to rotate. It's going to rotate by an angle. Let's calculate this angle. Let me call psi the integral over delta k times dz. And the phase shift between the two is twice as large, and then the rotation of the plane is going to be by this angle here. So this will be, if I just factor out, this is wrong. The NE belongs in here. Okay, we have 2 pi e cubed divided by MEC squared, 1 over omega squared, but now an integral over NE times B times dz. Now this works only if magnetic field and propagation direction of the electromagnetic wave are aligned. So what matters here is the z component of the magnetic field if you have others. Okay? And this quantity here is called rotation measure. Right? This is the angle by which the linear polarization is going to rotate. All right, so it's quantified by this number here. But what it tells you is how much magnetic field aligned or opposed with your line of sight you're collecting as you propagate through the plasma, weighted by the electron number density. Do you remember the dispersion measure that we had when we looked at a thermal plasma? That's Ne times E, right? So very similar to what we found there. There's a rotation measure as we had a dispersion measure there, and the rotation measure tells you by how much the polarization direction is going to rotate. Now this is a very, very, yeah. And that's exactly what I mean, because I'm now integrating along the z direction of my coordinate system. It would be a parameter along the line of sight. Yeah? It's not redshift. All right. So this is a very important diagnostic of magnetic fields in plasmas, and I will show you examples. Now, how do you make sense of that? Suppose you take an image of, let's say, a huge distribution of plasma. That could be the Milky Way, right? Our home galaxy. That could be a galaxy cluster or whatnot, right? And you're looking through that plasma at radio sources that emit polarized radiation. That seems like a lot of conditions, but remember what the main source for radio emission is. It's synchrotron radiation, which is naturally polarized and naturally linearly polarized. How nice, right? So very many radio sources that we have in the first place do us the favor of emitting polarized light by nature. That's beautiful. So what we see is the polarized radio emission, and do you remember the synchrotron spectrum? It's very broad, and it has no lines. So you have a broad continuum that is shining through the plasma with polarized light. How convenient! Because this means that, depending on the frequency where you observe, you will see a lot or less or even less Faraday rotation if you go from low to high frequency. So you start with a low frequency, you see the polarization direction somewhere. You go to higher and higher frequency and the polarization direction is going to turn. This is the strongest evidence for a magnetic field to sit in the middle. Okay? And then by the slope of the curve that you get if you measure the polarization angle as a function of frequency squared, sorry, you get the rotation measure. This doesn't tell you what the magnetic field is, of course, but it tells you at least what the electron density times the magnetic field is, pointing towards you. And then you can make all kinds of arguments, right? Saying that, okay, I'm assuming an isotropic magnetic field. Then you are lost, right? Because then you integrate over random directions of the magnetic field and no signal will remain. But then you can look at the dispersion of that, at the variance of it, and then you will measure indirectly the energy density in the magnetic field, and so on and so forth. There will be a problem about this. Okay, very important, Faraday rotation. Magnetic birefringence of a plasma. Okay, and so important for diagnostics of magnetic fields in the universe. Now let me show you some results. Let's have a look at our Christmas decoration, the galaxy M83, discovered in 1751. Not exactly as pretty as it looks here. This is an image taken with the ESO wide field imager in La Serena in Chile. Very beautiful, right? You see in red star formation regions and so on. And it's a spiral galaxy that is supposed to be very similar to our Milky Way, a barred spiral galaxy with not too many arms. Lovely. Okay, now, there happen to be radio sources behind it. So you can measure the Faraday rotation. And here it is. So the lines show you the radio intensity. Forget about it. The colors show you the Faraday rotation. And you see, unfortunately I forgot what frequency they measured at, but nonetheless you always need to measure Faraday rotation at several frequencies, right? Because otherwise, yeah, you know that. Right, now, that goes from minus 40 to plus 40 radians per square meter. Why per square meter? Well, that comes from the 1 over frequency square scaling of the rotation measure. So this is not a small effect, right? It's pretty strong. You have positive and negative signs. What do they mean? Well, the magnetic field can point towards you, it can point away from you, right? So you get a sense of the orientation of the magnetic field as well, relative to your line of sight, which is of course against the wave vector of the electromagnetic radiation. All right, and then you see all these fluctuations here. Then you can calculate a correlation length. You can estimate the magnetic field strength. You would need an estimate for the electron number density there. How could you get that? from Bremsstrahlung radiation, for example, right, which does not know anything about the magnetic field, but does know about the square of the electron number density. So you need to combine observations and so on, and as all the time in astronomy or astrophysics, you need to speculate about the 3D geometrical orientation of this magnetic field, and then you can get a lot of constraints and estimates out of that. And apart from that, I find it fascinating how the magnetic field is, or the magnetic field strength, is correlated here with the arms of the spiral galaxy. However, the most beautiful thing I found in terms of Faraday rotation is this full sky map. What does it show you? It's the magnetic field of our galaxy. Right? Because what are we doing here? We are looking, in this case, with a low frequency array, with a low-far telescope into the sky. Have you seen LOFAR? It looks like a garden fence. Individual radio antennae like this, and you have soccer fields of them. And you have many of these soccer fields spread around Europe. And so you have the possibility, if you have a really strong computer, to cross-correlate the signals that all of these garden fence or these rods, right, spread across Europe receive. And then by changing the phase shift of the signals or by filtering the phase shift between the signals that you see in different of these garden rods, you can choose where you look. Amazing. Takes a lot and a lot of computer power nonetheless, but yeah. So people have used LOFAR in order to measure Faraday rotation of all radio sources that were strong enough that they could find on the sky. And there are quite a lot. And so you get a full sky map. Of course, right? Every radio source that you can observe for its Faraday rotation this way will give you a single point-like signal. So you can create a map from that only if you smooth the signal sufficiently. Okay, but the number of radio sources in the sky is high enough so that the smoothing is not too strong. So you can see a map of the radial direction of the magnetic field of the Milky Way measured from Faraday rotation. Okay, that's about 200 rads per square meter, not 40 like we had before, right? Minus 200 rads per square meter. Okay, this is very low frequency. Remember, we had a signal that goes like 1 over omega. So low frequency helps, right? Low frequency increases the rotation. On the other hand, we need to make sure that we still satisfy our propagation conditions here, right? That omega is very much larger than the LAMO frequency and the plasma frequency. All right, that's the case. Now, minus 200 plus 200 rads per square meter. And we sit in the middle of the Milky Way, and we can look at the Z component, the radial component of the magnetic field strength all over the sky. These are results, as you see, published in 2022, so relatively new. And I just think this is a spectacular image. Spectacular image. Okay. So much that I wanted to say about propagation of electromagnetic radiation through a magnetized plasma, magnetic birefringence, and the Faraday rotation that it leads to. Right? We saw that we have to split the dispersion relation into a branch that has omega plus omega L, the LAMO frequency, and omega minus the LAMO frequency. And this tells you where this optical birefringence is coming from. Namely, if you have a preferred direction, if you have a certain direction of the magnetic field and you fly with or against it, then this imprints a certain sense of rotation on the motion of the electrons, the plasma electrons, just by the orientation of the Lorentz force. So it does matter if you try to move the electrons with the Lorentz force or against it. And this gives rise to this birefringence effect here. That allows us to find out so much about magnetic fields in things, galaxy clusters, Milky Way, whatever. Okay, so far so good. Time for the break. And then for something completely different. Schneller ist kein Weg, ne?
Wir waren ja von einem Teil des Plasma ausgegangen und das haben wir jetzt quasi die Informationen.
Time to move on. Now it's time for fun with waves. Where are we? We have been here now, waves in magnetized cold plasmas, and the goal that I wanted to reach was to discuss Faraday rotation, and to explain where it's coming from and how you quantify it. Okay, nice. Now I skip over a lot of detail and I directly go to the section on hydromagnetic waves. Okay, so the point is, we have seen that magnetic fields act back on the flow of the plasma, and the flow of the plasma changes the magnetic field. Are there wave-like solutions? Remember, when we looked at perturbations of the ordinary hydrodynamical equations without magnetic field, we saw that the pressure perturbations give rise to sound waves. Now let's essentially repeat the same story with a magnetized plasma, because the additional forces that come from the magnetic field must in some way, of course, also act back on fluctuations in the plasma. And then we should at least expect different sound speeds depending on whether we are going with or against, or however, the magnetic field. Let's see what comes out, right? And what comes out is a whole zoo of possible sound waves. And in fact, you will see that we will encounter 3 different sound speeds, plus the thermal sound speed that you know already. So you expect plasmas to be full of different types of waves. And of course, all of these waves can become unstable. And this is one reason why I don't believe that plasma fusion will ever reach the level of being useful, except for fundamental research. Okay, that's the point. Now, let's have a look at that. What do we have to do? As always, right, we follow the recipe for stability analysis. What was that? We take the relevant equations, we introduce perturbations, we linearize them in the perturbations, we decompose them into the perturbations into plane waves. Therefore, we get a relation between frequency and wave number. So we have a dispersion relation. And for stability, we look for positive frequencies squared. Same procedure as every year. But before we do that, let me introduce one piece of notation. But first of all, let me take this double vector product here and write it in a different way. You know the Grassmann identity, right? That allows you to say this is A times C times B minus A times B times C. Okay, good. Let me not ask who wants to see that, because I don't want to show it once more. All right, now I want to write this as a matrix times a vector C. This is what I want to have, with a matrix in parentheses. This term is easy, right? This is just the scalar product of A times B times the unit matrix. Okay, what do we do with this? I propose that. Okay, because if I take this matrix here, this tensor product between B and A in this order, by the rules of matrix multiplication, this will lead to the scalar product of A times C, and then the direction will be set by the vector B. Okay, I will need this matrix representation of the Grassmann identity, that's what it is, as we move along. Okay, now what are the relevant equations? Do you remember? This one was easy. By the way, if I had a chance to travel back in time sufficiently long, one of the scientists I would like to meet would be Michael Faraday. Maybe even before Maxwell, because everything what I read says he was an extremely amiable person and such a genius in finding out things. Eh? Amazing. Okay, but this one is Maxwell, nonetheless. Okay, B dot. Now, I'm going to use the induction equation without sources and without the diffusion term. Okay, so I'm assuming infinite conductivity, or in other words, an ideal plasma. Or, if you want to phrase it yet differently, an infinite magnetic Reynolds number. All these statements mean the same thing. So what is it? It's the curl of V cross B. And sigma to infinity enters here, conductivity. Okay, what else? Mass conservation, of course. What else? We need this beautiful thing. So up to here, it's Euler's equation without gravitational field. And this one is the term that we had nicely decomposed into two contributions, right? Magnetic pressure and the term that shows that magnetic fields want to be straight. And for simplicity, I'm going to ignore the gravitational part. What else? Now, we have one equation here. We have three equations here. We have one equation here. We have three equations here. That's 8 equations. How many variables do we have? We have 3, 4, 7, 8. There should be one missing. Anyway, and we are going to relate, as we did before, the pressure fluctuations that we will encounter to density fluctuations. All right. Now, these are the relevant equations for these quantities over here. Now we proceed exactly as written in the cookbook. We introduce perturbations. So, we will have fluctuations in the magnetic field. I'm going to analyze the perturbations in the rest frame of the fluid so that V0 is 0. This I can do by any Galilei transform. Then I have fluctuations in the density. And of course, I will also have fluctuations in the pressure. And for the pressure fluctuations, I'm going to write that these will be Cs squared times the density fluctuations, and Cs squared is the ordinary thermal sound speed that you know, derived, for example, under adiabatic conditions, in which case it would be the square root of gamma times P over rho. Okay, now how far do we get with that? Of course, the unperturbed solutions, B0, rho 0, P0, must also satisfy our equations. So if I ignore the perturbations altogether, then I need to get solutions anyway. So I know that the divergence of B0 independently must also be 0, so the divergence not just of the sum, but of the perturbation alone of the magnetic field must also be 0. So I can write this. Okay. Now look, if I look at the induction equation and I insert the velocity as decomposed here, then all I can insert here in the induction equation is the velocity fluctuation delta V. So this term would already be of first order in the perturbation. So then I only can multiply this vectorially with B0 in order to remain at first order. And I will get the time derivative of delta B over here. All right? And at first order, of course, at 0th order, it just means that B0 dot is 0. And this means that the background, the unperturbed solution of the magnetic field must be constant in time. Okay, so induction equation looks like delta B dot is the curl of delta V cross B0 at first order, right? And that's what we do. We want to linearize in the perturbations. Same here, you know that, right? If I insert for the velocity delta V, then this term is first order, then I need to multiply it with rho 0 in order to get the time derivative of the density perturbation. So delta rho dot must be, let me write it this way, plus divergence of rho 0 times delta V must be 0. Okay, and again, it tells me that rho 0 must be time independent, right, at 0th order. All right, now what do we do about this thing here? This contains a square of the velocities, but we do not have a background velocity anymore, so this would be at the lowest of second order, so this goes away altogether. How nice. Then, the unperturbed velocity V0 must remain 0. So this means that there must be no gradient in P0. And this must also vanish here for B0 alone. So this means that the curl of B0 must also be 0, right? That's the 0th order solution here. Okay, but at first order, this means that delta V dot plus nothing equals, now minus. I'm going to write Cs squared gradient delta rho, assuming that the sound speed is spatially constant. Okay. Now, I have a first order term in the numerator, therefore the denominator must be a 0th order solution. Rho 0. Okay, here we said that the curl of B0 must vanish. So the only non-vanishing term that I can start with here is the curl of delta B. But then this must be B0 only. And this must be rho 0 in order to keep the term at first order. So then this is plus 1 over 4 pi rho 0 times the curl of delta B times B0. Okay. This is now our linearized set of relevant equations. Cookbook step number 2. Now we go to cookbook step number 3, that is decomposition of the perturbations into plane waves. Aha. The divergence means multiplication with I times k, I times the wave vector. I cancel the I to get k times delta B. And again, I'm using the misnomer that I use the symbol delta B both for the fluctuation in the magnetic field and for the amplitude of its plane waves. Okay, in other words, the wave-like perturbations have a wave vector that is always perpendicular to the magnetic field perturbation. So if the wave goes this way, the magnetic field goes this way. Okay, how about that? A time derivative gives you minus I omega. The curl gives you a plus I k cross. The I cancels, so we have minus omega times delta B equals k cross delta V cross B0. Time derivative gives you minus I omega. Divergence gives you plus ik. I cancels, so we have minus omega delta rho plus k times, let me write this differently, rho 0 k times delta V equals 0. And finally this one, again, minus omega delta V due to the time derivative in the first term. And then minus cs squared over rho 0 wave vector k times delta rho. Plus 1 over 4 pi rho 0. Now, k cross delta B cross B0. Okay. Looks good, doesn't it? Now, the next step will be that we use this matrix representation of the Grassmann identity. This thing twice, right? Once here and once down here. What will this give us? Well, first of all, you see from the continuity equation, you can conclude that delta rho over rho 0, as you need it here, is given by k times delta V over omega. Okay, so this means that we can eliminate delta rho in the Euler equation and have the first two terms here contain delta V only. Now, from the induction equation, we can conclude that delta B must be minus 1 over omega K cross delta V cross B0. In other words, I can replace delta B by an expression that contains delta V only. So then I'm here. So this means that the goal is now to use all these other equations just to replace delta rho over rho 0 and delta B by expression times delta V. Okay, and then we get a 3 by 3 matrix equation for delta V, and we can be confident to solve that. Okay, so let me first of all use the this relation here for delta rho over rho only, and bring the Euler equation, the last equation here, in this form, minus Cs squared times K. Okay, now delta rho over rho, so this is K times delta V divided by omega. So there is one scalar product with a wave vector K, but there's also a wave vector K remaining. This cries out loud for a matrix representation, right? That's just K tensor K times delta V. Okay. Now, let me introduce a minus sign here, because I want to change the order of these factors here. Because then they are in the standard form for the Grassmann identity, and I can use directly this, this representation here. But let me write it down first. So that's B0 times, or cross K cross delta B. Okay. Can get rid of these minus signs. Now I'm multiplying by omega first of all. And yeah, I get omega times delta V is Cs squared and let me write the next term already as K tensor K times delta V. So now I'm here. Now I'm going to use the matrix representation of the Grassmann identity. And first of all, this means that I need the tensor product of second times first factor. Second times first factor, so this is K tensor B0. And then the scalar product of first times second. So this is K times B0 times the unit matrix, multiplied with delta B. Okay. Now let me pull the factor of K and B, a scalar factor of K and B out of this, of these parentheses here, these brackets. And write omega squared, omega squared delta V, yes, equals C squared K squared. Now, K unit vector tensor K unit vector times delta V plus 1 over 4 pi rho 0 K times B0. And now k times b unit vectors minus k times b scalar times the unit matrix times delta b. Now you see, now we have a scalar product between k and b, so this boils down to having the cosine of an angle in between them. Let's call it cosine psi this time. Okay? All right, so far so good. Now we need an expression for delta b. So I'm interrupting our treatment of Euler's equation at this point, and I'm returning to the induction equation in this form up here. So now I'm going to reconsider delta b equals minus 1 over omega k cross delta v cross b0. Aha. Let me take plus here. K cross b0 cross delta v. Okay, so I'm using the antisymmetry under exchange to change the sign here. And then I can bring, or I can use the matrix representation of the Grassmann identity again. So it's 1 over omega b0 tensor k, second factor times first, minus k times b0 again times the unit matrix in 3 dimensions, now times delta v. Okay, and again I can factor k times b0 out, and I get delta b is k times b0 divided by omega. Now b tensor k, here we had k tensor b. That's a transpose, right? They are transposed to each other. Aha. Must not confuse them. Again, here we have then the cosine psi times the unit matrix times delta v. Notice I haven't fixed the coordinate system at all, right? The only thing I needed so far is the relative orientation of the unit vectors k hat and b hat, and they are just fixed by a cosine. Okay, now with this expression here, I'm going here. Okay. Omega squared delta v equals cs squared k squared k hat tensor k hat times delta v. Aha. See, now we have made a mistake. Not you, I did. I wanted, from this to that step, I wanted to multiply with omega. I did here, I did not here. So there's a factor of omega in here. So this means there's a factor of omega in here as well. But then there's a factor of 1 over omega and it goes away. That's what I was missing. Okay, right. Then I have plus, the omega is cancelled, but the kb is squared, divided by 4 pi rho 0. Okay, now k tensor b minus cosine psi, the unit matrix, a b tensor k minus cosine psi, the unit matrix, times delta v. Look how nice, right? Now we just have a matrix equation for delta v. Just need to multiply the remaining part out here. So let me have a separate look at this matrix product, which now of course contains 4 terms. Let me start with the unit matrix. This will be cosine square psi times the unit matrix, the product of these two. And then I will have minus k tensor b times the unit matrix times a cosine minus b tensor k times cosine psi times the unit matrix. So this will give me minus cosine psi k tensor b plus b tensor k. That's the symmetric part of b tensor k. Right? This is the symmetrized part. I take the tensor k tensor b and I add its transpose. Okay, and finally, I need to multiply these two here. And if I multiply these two, then I get a scalar product of b hat with b hat, that's 1. And what remains is just a k tensor k. So plus k tensor k. Okay. Now let's collect things. But you see, this one goes like k square. This one goes like k square. So let me divide this by k square, the whole equation. And then I get an expression that is omega square divided by k square. This is a velocity. That's the phase velocity of our perturbation. So I call this ck squared, the phase velocity of our perturbation. Okay, then I get ck squared from here. And all the terms will get a factor of delta v, which I'm going to push to the end. But this one goes like the unit matrix. And if I pull the delta v away, then I have another term that goes like the unit matrix that comes from here. But this has this prefactor here without the k square because we divided this out. So let's have a look at b0 squared divided by 4 pi rho 0. Well, b0 squared divided by 4 pi is the magnetic pressure. So that's a pressure divided by a density. So that's another velocity squared. It's called the Alfvén velocity. Ca squared. Okay. So I can just subtract Ca squared times cosine squared psi from here with this prefactor. And then I have everything together that is multiplied with the unit matrix. Okay, now let's take care of the terms that go like k tensor k. Then I have from here a minus cs squared, and I have divided by k squared, so that's it. And I have another k tensor k over here, which comes with a minus Ca squared. And then we have this mixed tensor here, symmetrized. It comes with a negative sign. So if I bring this to the other side, I get a plus. I get a Ca squared from the amplitude, a cosine psi from here, And now k tensor b plus b tensor k. That's it. No more than that. Times delta v must be 0. So if we now take the determinant of this beautiful matrix, and this will be much easier than it looks like, we will have our dispersion relations. And you see, there are several velocities characterizing the whole thing. There's the phase velocity of the perturbation. There's this velocity ca square, Alfvén velocity, named after Hannes Alfvén, who got the Nobel Prize, I think, in 1971. There's the sound speed. Now, let's see. Now, in order to evaluate this determinant, I choose a particular coordinate frame. And I'm choosing a coordinate frame in which k, watch out, points along Ex. Not Ez, Ex. Then I need to introduce a unit vector for b hat that has an angle psi, because we already fixed that, with respect to k. And it must be unit vector. And I'm now going to orient the coordinate system such that the vector b falls into the xy plane. And in other words, I'm rotating around the vector k until b finally falls into the xy plane. So then the b hat looks like cosine psi sinus psi 0. No restriction of generality made. Now, you see then k tensor k is this. K tensor b plus b tensor k. K has a single non-vanishing component. So k tensor b has cosine psi as its first, as its 1,1 argument, and b tensor k the same. So this is going to be 2 times cosine psi. Then along the first row, I will just repeat the first row of k tensor b. I will just repeat the components of b. So this will be sine psi 0. And from the transpose, I will get the same entry here. And nothing else. All right, so you will get the vector b once along a column, once along a row, and you will have to sum over both, and that's it. Okay, now let us assemble all the terms that we get. I start with a 1,1 component. Here I get this from the unit matrix. This one only has a 1,1 component. So I can just run through. And this one adds 2 times cosine squared psi times ca squared to the 1,1 component. Aha. The 1,1 component really wins. So we have ck squared minus ca squared cosine squared psi minus CS squared minus CA squared. And finally, plus 2 times cosine squared psi times CA squared. That's our 1-1 component. But you see, you can simplify it. All right. A 1-2 component. This one doesn't add. This one doesn't add. This one adds a CA squared cosine psi sine psi. And we have no 1-3 component. Okay. The 2-1 component. Nothing from here. Nothing from here. And the CA squared cosine psi sine psi from the last term. Okay. The 2-2 component. Well, now we have a contribution from the diagonal and none from the others. Okay. CK squared minus CA squared cosine psi 0. Then we have zeros all along, except for this term from the diagonal. So all right. So that's the complete matrix. Times delta V must be 0. Now we need the determinant. But before I calculate the determinant, let me simplify, because the 1-1 component can be simplified. So first of all, you see here we have CK squared minus CS squared, these two terms. But now we have minus CA squared cosine squared psi plus 2 times CA squared cosine squared psi. That's 1 times CA squared cosine squared psi minus CA squared. So this is minus sine squared psi CA squared. All right? Good. Here we have CA squared cosine psi sine psi 0. Here we have CA squared cosine psi sine psi. Here we have CK squared minus CA squared cosine squared psi. And we have the same here. All right, this is the final result. And you see from here that we will have at least 3 types of velocity perturbations. One type will have a z component only. Right? If I look at eigenvectors here, with eigenvalue 0, then if I have delta V z different from 0, but in other words, if I have a velocity perturbation that now looks into the z direction, where neither k points nor b points, right? That's perpendicular on the planes spanned by k hat and b hat. Then we have a dispersion relation which just says Ck equals plus or minus Ca times cosine psi. All right. I'm going to say a few words about this and then we finish for today and continue on Wednesday. first of all, this is the phase velocity. This is plus or minus the Alfvén velocity, but with a factor of cosine psi in addition. Suppose k and b are perpendicular to each other, then cosine psi is 0. Then this is a standing wave. The phase doesn't move. But what is its group velocity? The cosine psi here is the scalar product of b times k. So in other words, if I want to know what is the omega with respect to dk, all right, and remember ck is just omega divided by k. So this is d dk of plus or minus ca b unit vector times k wave vector. If I take the derivative of that with respect to k, I get plus or minus ca times b. So the group velocity points into the direction of the magnetic field. The phase velocity, of course, points into the direction of the wave vector. That's what the phase does. Right? So you have a situation in which, irrespective of the angle between k and b, physical information that is carried by these Alfvén waves here is flowing along the b direction. The phase may or may not be moving into the k direction. That's really weird, right? And so on and so forth. Now, let us stop right here. These are velocity perturbation like that, called Alfvén waves, right? And they are the first very peculiar waves that you can have in a plasma, right? Phase is moving into one direction, group velocity is moving in another direction. Phase velocity depends on the orientation between these two vectors, group velocity does not. This is always the Alfvén speed. This is the Alfvén speed times the cosine psi, and so on and so forth. Right? Very interesting plasma waves. And then on Wednesday, we are going to look at what remains in 2 dimensions, right? In the two-dimensional plane spanned by k and b. And there we will still get a whole continuum of different sound waves. All right? This is how far I wanted to get. Sorry for running over time. But stopping right in the middle of an Alfvén wave leads to immense heating, right? So we should get out of that. Okay. Then see you on Wednesday. If I do not see you on Wednesday, I wish you a Merry Christmas, but I hope to see you on Wednesday. All right. Enough for today.